Hello, my name is Sanika Kurude, and this is my Circuits Lab 3. So the purpose of this lab was to understand how components in a circuit work by recording observations on a real circuit. The models that we had was a circuit with two 1.5 volt batteries, two resistors, and two ammeters, and then a second circuit with two 1.5 volt batteries, two light bulbs, and a capacitor. So the physics principles that we used in this was that the voltage is equal to resistance times the current. The voltage in the voltage at the start is equal to the final voltage, which is also the same as V total equals 0. And the reason that we use this was basically to calculate the voltage drops across each of the different components in the circuit and to basically understand the difference between experimental and calculated data. So the main result was that the experimental circuit was slightly off compared to the calculations, and I'll talk about that soon. So the series circuit, the system was just the circuit and the surroundings was nothing because it's supposed to be a closed circuit. The initial conditions is a 47 ohm and a 100 ohm resistor, and the voltage was 3 volts because of the two batteries. And the assumption that we had before was that the circuit across both resistors would be 0.02 amps, since 3 volts divided by the total resistance, since it's in series, is 147. So the data that we collected was in the initial circuit, the voltage drop across the first resistor was 0.0188 amps, and the second one was 0.0188 amps. It was the same for both. And if you reversed it, the I would just become negative. When we put the voltmeter into the circuit, the voltmeter read 3 volts and the ammeter read 0 amps, and this is because the high resistance of the voltmeter alters the current flow when you're breaking into the circuit, which will make the current read 0. So when you place the voltmeter outside of the circuit, the ammeter doesn't change because you're not breaking into the circuit. The initial voltage was 0 volts. The voltage drop across the 47 ohm resistor was 0.9 volts, and the voltage drop across the 100 ohm resistor was 1.9 volts. And when you add that together, it's 2.8 volts, but technically it should add up to 3, but because it's not a perfectly closed circuit, there is some loss due to the wires and the ammeter itself, which we'll get to eventually. When you replace the voltmeter with an ammeter in parallel, the other ammeter increases its reading from 0.0188 amps to 0.0497 amps, and this is because ammeters have low resistance, which causes more current to flow through it rather than the resistor, so it reads a higher current than previously. And then finally, calculating the resistance across each of the components. So for the 47 ohms, I just did the voltage drop that we found using the voltmeter and divided that by the current and got 47.87 ohms, which is pretty close to what it actually is. For the 100 ohm meter, I got 100.06 ohms, which again is pretty close. And this is the wires and the ammeters. This shows why the voltage drop across just the two resistors doesn't add up to 3, because some current goes through the wires and ammeters since they have a little bit of resistance. So we calculated the resistance of all of the wires added up to be 1.6 ohms and the resistance of the ammeter to be 3.99 ohms. So when you add all of those voltages together, you get 2.905 volts, which is closer to the 3 volts that it should be. And in the corner is my graph showing the voltage across all of the resistors and ammeters. So in the RC circuit, the system was a circuit and there was nothing in the surroundings again, and the initial conditions were one 10 ohm light bulb and one 1 Faraday capacitor. So the data that we found was that when the capacitor was charging, the bulb was on and then it dimmed out fast, and it took about 63 seconds. And when the capacitor was discharging, it started out brighter and dimmed out as the capacitor discharged, and that took 57 seconds. So we found that the capacitor discharging took less time than charging, but both of them were pretty much the same amount of time, so it could just be a human error that caused some issues. The calculations that we made previously were pretty much similar to the data that we observed. Like I said, our calculated current was 0.02 amps and our experimental current was read as 0.0188 amps, which is a 0.0012 difference, which is not that much. And our voltage should have been 3 volts, but we actually calculated to be 2.905 volts, which is about a 0.095 volt difference, which again isn't a large amount. So some sources of error are that since it isn't a perfectly closed circuit, we could have lost some current or voltage due to some outside force, and we also could have timed wrong during the RC circuit. If we charge the capacitor with no resistor in the circuit, in theory it would charge instantly because there's no resistance to limit the current flow. But in real life, since we just saw, it's impossible to have an ideal circuit because even without a resistor, the wires and battery have some small resistance that will limit flow. So when without any resistors, the light bulb would just it would charge very like a time slightly larger than 0. Um, but technically, without any resistance, it should charge immediately. Thank you so much for listening. Bye.